All right, we're going to start 5.2 now. We're going to talk about the addition rules of probability. We briefly talked about them a little bit in 5.1 when we had some of those ors. But today we're going to get much more into it and kind of define it better. So first we needed some definitions. The definition we're going to use first is called mutually exclusive. That means two things share no common outcomes. Another phrase or another term is disjoint. That's when two events don't contain any of the same outcomes or events. So an example of two disjointed events are if event A is rolling a 5 and event B is rolling a 1 or a 6. Those are disjoint. There's no way of being in both A and in B. So do those two events have anything in common? No, they do not. What about rolling a 3 and rolling an odd number? Are those mutually exclusive? No, they are not mutually exclusive. 3 is an odd number. So because 3 is an odd number, these are not mutually exclusive, which leads down a different path when we start talking about or probabilities. So if we are drawing a Venn diagram of mutually exclusive events, we want it to look like this, where A and B are totally separate. There's no overlap here in the middle. They're totally disjoint, meaning not connected. When we have mutually exclusive or disjoint events, the addition rule is very simple. If we have the probability of A or B, it's simply the probability of A plus the probability of B, which makes it very easy. So find the probability that a randomly selected integer between 1 and 10 is 3 or 7. First of all, is event, let's label our event. So we have A is a 3, B is a 7, are A and B mutually exclusive? Yeah, they are. You can't have both a 3 and a 7 in one number. So they are, in fact, mutually exclusive. So then if we're trying to find the probability of A or B, we take the probability of A and add it to the probability of B. So how many different ways can you get a 3? One way. How many different ways can you get a 7? Also one way. And so that gives us 2/10. And we always reduce. And so our answer is 1/5. Next, a box contains 3 glazed donuts, 4 jelly donuts, and 5 chocolate donuts. Find the probability of selecting a glazed or a chocolate donut. First, are they mutually exclusive? Yes, it does not say anything about chocolate glazed donuts. Only glazed and chocolate, so those are separate things. So we have event A, which we'll call glazed, and B, which will be chocolate. We are trying to find the probability of A or B. It's the probability of A plus the probability of B divided by, or just the probability of each of those added together. So we have 3 glazed donuts out of a total of 12 donuts, plus the 5 chocolate donuts out of 12 give us 8 out of 12. And again, we always reduce. Now, there's going to be cases where the numbers are not, or the events are not mutually exclusive. We ran into that when we did the 3 of diamonds. 3 of diamonds, or the picking a 3 or a diamond, was not mutually exclusive because a 3 of diamonds is both a 3 and a diamond. And so we had to add this last piece into our formula, which was subtracting the duplication. So probability of A and B means what is the overlap? How many events are in both event A and event B? How many outcomes are there? If it's mutually exclusive, That answer is 0. If it's not mutually exclusive, that's something that we have to go back and figure out. So if we have Venn diagram of non-mutually exclusive events, the intersection is A and B. The union is A or B. And so union is sometimes with a big U, intersection is sometimes with that letter there. So when I'm writing my probability statements, instead of ands and ors, I will sometimes use this notation. That notation comes from logistics and logic classes. So you'll see those if you take a logic class in college. All right, now let's use a two-way table to discuss some probabilities. So first of all, are these things mutually exclusive? Excuse me. No, they're not. So that means we're going to have to be doing some adding and some subtracting depending on what questions and what outcomes we're looking at. So first, it's a two-way table because if we look horizontally, it talks about the number of people that smoke cigars and whether they never smoked, they used to smoke, or they currently smoke. And if we look vertically, it talks about whether someone died of cancer or did not die from cancer. So those are the two different things this two-way table talks about. So let's start off. What is the probability that he died from cancer? So we're going to call died from cancer A, and we are trying to find the probability of A. So how many people died from cancer? We look at this column here, and we get 1,014 divided by the total number of people in this study, which is 137,243, and we see that that probability is 0.00739. Next is, what is the probability that he was a current cigar smoker? So we're going to call that B. So what is the probability of B? Well, current cigar smoker, we're looking that way. So we have 7,866 divided by, again, the total number of people. And this we get 0.05731. Now in part C, we're starting to get into our ands and our ors and things like that. So what is the probability that he died from cancer and current cigar smoker? So that is the probability of A and B, or probability of A and B. Well, in this case, we go back up here to our table, and which number got circled twice? That is the number that got circled twice, so that is our overlap. That is the and part of this. They died from cancer, and they were a current cigar smoker, and so we get 141 divided by, and again, 137,243, which is 0.00103. All right. Part D, probability that he died from cancer or current cigar smoker. So now we're looking at the probability of A or B. So probability of A or B. Now we use that formula that we just talked about. This probability is equal to the probability of A plus the probability of B minus the probability of A and B. So A, B, and C, we're finding those three different parts. So we have 0.00739 plus 0.05731 minus 0.00130. And that gives us our final probability. So the probability that he died from cancer or was a current cigar smoker was 0.06367. And then last, what is the probability that he did not die from cancer or never smoked? So we'll switch it up. A is now he did not die from cancer, and B is now never smoked. So again, going up here, did not die from cancer. Never smoked. And then the overlap is that square there. So probability of A or B, probability of A plus probability of B minus probability of A and B. I'm sorry, I flip between using ors and ands and then the union and intersection symbol. They mean the same thing. Sometimes I'm lazy and I don't want to write ands and ors, so they mean the same thing though. So try not to get confused. If you have questions or get confused, let me know and I'll try and clear them up for you. So we have 136, 229, and then all of these are divided by the same number. So probability of A, probability of B, probability of A and B. We add the first two, subtract the second one, and then we get a probability of 0.99831 is the probability that they did not die from cancer or that they never smoked a cigar. All right, next problem. Consider a family with 2 children and suppose the probability of having a boy and a girl are the same. That's not actually true. The probability of having a girl is actually slightly higher than the probability of having a boy. But for this class, we're going to assume that it's always 50-50, when in fact it's not. It's closer to like a 52-53 to 47-48 type of thing. So let's go through and look to see how we can do this. So consider a family with 2 children and suppose the probability is the same. Define event A is having a girl on the first birth, so change that. A is girl on first birth, and B, girl on second birth. We want to find the probability of A or B. So let's go through and come up with our probabilities. So probability A. What's the probability of having a girl as your first child? Well, we just said the probabilities were equal, so that's 1/2. Probability of B is also 1/2. Now, are those two events mutually exclusive? Is having a girl on the first birth and having a girl on the second birth mutually exclusive? Think about it. If you're not sure, rewrite our sample space. So remember, we talked about this before. Our sample space of having 2 kids, boy, 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 girl, girl, boy, girl, girl. So is having a girl on the first birth and second birth mutually exclusive? No, it's not, because this last one, girl, girl, is both. We're double counting that one. So it's not mutually exclusive. So that means the probability of A and B is 1/4. So now if I want to find the probability of A or B, probability of A plus the probability of B minus the probability of A and B, 1/2 plus 1/2 minus 1/4. So the probability of having a girl on the first or the second birth, 3/4. All right. A single card is drawn from the deck. It's find the probability that it is a jack or a 7. So A is a 7, B is a jack, and we are finding the probability of A or B. So probability of A or B, there are 4 7s and there are 4 jacks. So that gives us 8 out of 52, which gives us 2 13ths. A king or a club. Again, A is a king, B is a club. Probability of A or B. There's 4 kings. There's 13 clubs. But unlike the 7 or jack, there is an overlap. We talked about this in 5.1. There is a king of clubs, so we have to subtract that king of clubs. And that brings our total to 1650 seconds, which is 4 13ths. All right, the next thing we're going to talk about in 5.2 is the complement rule. So the complement with an E, not an I, refers to everything that is not the event. So in here you see we have our Venn diagram where the rectangle is our sample space. Inside of our sample space, we have this circle here, which represents the probability of our event E happening. Everything else is the probability of not E. So when you see E to the C, that is pronounced, that is equal to not E. So that means everything is in either E or not E. So the probability of E plus the probability of not E is always equal to 1. So keep that in mind. Sometimes it's a lot easier to find the not probability than it is to find the actual probability you're looking for. And so using these complement rules is very helpful. So here we're going to go through, I'll do the first one and then pause the video, go through and see if you guys can get the rest of them. So we're going to roll a die and we're going to get a 4. So what is the event? The event is rolling a 4. What is the complement of that? The complement of that is rolling a 1, 2, 3, 5, or 6. It's everything that's not a 4. So what's the probability of E? 1/6, because there's one way of getting a 4. What's the probability of not E? 5 out of 6, because there's 5 different ways of getting not a 6. All right, pause the video and figure out the rest of these and then unpause when you're done. All right, and so there you can see all of them. For B, selecting a vowel, there are 5 vowels, A, E, I, O, and U. And the complement of that is selecting a letter that is not a vowel or that is a consonant, and there's 21 of those. Selecting a month and getting a month that begins with J, January, June, July, or not a J, and that's the complement. And then D is the same thing. Next, assuming that all 365 birthdays are equally likely, what is the probability that the next stranger you meet will not share your birthday? Well, let's say event A is same birthday. Well, what's the probability that you share a birthday? So, same birthday. Well, the probability of A is, well, how many birthdays do you have? Well, you only have 1, so the probability of A is 1 over 365. Now, what's the complement of A? You have a different birthday. How do we find the probability of that complement? Well, the probability of that complement is equal to 1 minus the original probability. And so that gives us our answer of the probability that this next stranger you meet will not share your birthday is 364 out of 365, which is 0.9973. All right. Finishing up, we have 2 more examples. Suppose you did a survey to determine if people like the taste of a new soft drink. The results are below. Find the probability that the person did not respond no using the complement. So using the complement, that means responded no is our A. And the probability of A is 8 over 25. So the complement of that means they responded not no. And in this case, not no means yes or undecided. So that means the probability of that is equal to 1 minus the original, which gives us 17/25. Last, if the probability A if A is having a girl, then not A is having a boy. Probability of A is 0.47. The probability of not A is 1 minus 0.47, which is 0.53. So the probability of having a boy would be 0.53 because you're either having a girl or a boy. That is the end of 5.2.